You might have wondered why we took a certain Legendre transform of the Hamiltonian when I previously remarked that there is a whole class of Legendre transform for any certain function which depends on a certain class of variables. Like again, we if we recap what we did, we took the differential of the Hamiltonian like this, and we derived the equation of the total differential like that, like expanding in the general Legendre transform way. But we could have took the negative of all that. We could have done dl minus dpq, and we could have expanded the equations out, and we would have got the negative of our original Hamiltonian, like we defined earlier. And this would be true because we still have a new function h depending upon q and p rather than q and q dot, which we were thinking of getting rid of, and we were doing all this Legendre transforms for. Now there is only one reason why we did all that, because basically it makes physical sense. Because if you expand out this function over here, which is basically p q dot minus L. So L was basically P minus U, which is basically kinetic energy minus potential energy, and that is mv squared by 2 minus U in the very basic sense. Okay, so if we, and this term over here is basically mv squared. Now I'm going very basic here. We're again writing in the very simple terms what velocities and all that is. So if we just take the algebra as it is, we get mv squared by 2 plus u as the Hamiltonian, and this is the total energy of the system, which is very important in physics, obviously. But if we took the negative definition as over here, we would have got minus mv squared plus u, and that would have not made much of a physical sense. Why would we want a function to be like that? So that's why, to make some physical sense and to use it for a physics, we defined the Hamiltonian to be in that certain way. But there is a class of functions that some authors like to call Hamilton-like functions, and there's a good problem in Goldstein as well in the Hamiltonian mechanics chapter, where he says you to derive Hamilton-like functions which depend upon the generalized velocities and the generalized momentas total differential, and that's a very good thing to do, and it's a good exercise. But the basic meaning for doing the Legendre transform in this manner was to make physical sense. Thank you.